Hi, today I'm talking about LeetCode problem 1387, sort integers by the power value. Now what this problem asks you to do is to write a function that takes a range of integers and a value k, which I'll talk more about in a second. And it wants you to compute what they call the power value, and it's not the power value that you may be familiar with, not power as in the mathematical operation, but a power value that they define here. They want you to compute a power value for each value in this range, and then order the integers by their power value in the range, and then return the kth integer in that order. So let me show you my whiteboarding that I wrote out before I started this problem to kind of illustrate what's happening. So the function, or the problem, the test, is going to give you a low and a high. It's also going to give you a k, a low, high, and a k. And you're going to generate out all of the numbers. So I know this looks like 10, but it's really the word low. You're going to generate out all of the numbers in this range. Then you're going to compute a power value for each of the numbers. Then you're going to imagine you have a tuple, or a pair, of a number, we'll call it n, and the power of n. And you're going to sort all of the numbers in this range according to their power value. So you sort them by their power value, and then you return the kth pair in your list. So let me give maybe a small example of it. One of the examples they give is if your input was 12 for low and 15 for high, and I think they say 3 for k. So that's low is 12, high 15, and k equals 3. What they want you to do is say, okay, the power of 12 is what? And their rule for power is if the number's even, then divide by 2. If it's odd, then multiply by 3, add 1. So if we were figuring out the power for 12, we'd say, okay, that's even, so we're going to divide by 2, and we're going to count the number of times we have to do one of these steps. Even again, divide by 2, so our count is at 2 now. This is odd, so we're going to multiply by 3 and add 1. That'll take us up to 10. I wish I wasn't counting with tallies, but whatever. Here we're going to go 1, 2, 3, 4. In fact, I'm just going to change and now count with numerals. So let me clarify that this is our count and this is our in. This is odd again, so multiply by 3 plus 1, which takes us to 11. And our count is now 5. Odd again, multiply by 3 plus 1, 34, 6. Half it, 17, 7, and so on. I'm not going to keep doing this, but you can be assured that all numbers will eventually get back to 1. And when it finally does get back to 1, so ... when we finally do get back to 1 on this inside, whatever number we have here, we'll call it p, is our power. And so this p would be the power of our original input, 12. So we'd just come back here and write 12p. And then we'd figure out what the power of 13 is. And that would be another pair. Then we'd figure out what the power of 14 is, p14. And then we'd figure out what the power of 15 is, p15. And then we would sort this list. So this is a list of pairs. We're going to sort this list by the value in the second index. We're going to sort it by the power. And then once sorted by the power, we're going to return the kth 1, 2, 3, 4, k, the kth value in that list. And so, my approach to this is I'm going to write a power function to compute what the power of any given number is. I'm going to find all the powers I'm going to find all the powers of all the elements of all the integers in my range. I'm going to sort the list, and then I'm going to return the kth of the power list. You can see when I wrote this, I didn't quite understand. I thought I was just getting a list of the powers and then returning the kth power. But actually what you're doing is returning the integer that corresponds to the kth power. So let me walk through this in code now. Here is my getKth function. That's the function I'm required to write. But before I talk about that, I want to talk about the power function. So the power function is just how I'm going to solve the question, what is the power of a given number, according to this rule. And so I'm going to use two variables here. One is count. This is the number of times I'm going to have to follow one of these two steps. Key is going to start as n, and the reason for that is because I theorized while I was working on it, while I was thinking about potential problems with this, like what if it's a really big range and I have to compute a lot of powers? And even, when you look over here, it took me, I wasn't even willing to do it manually to compute the power of 12 because it was going to take so many steps. So what if I had to compute the power of a really big number? And so to kind of safeguard against that, what I did is I realized that I could store a dictionary, which I'm calling memo in my code, and see if I've ever looked at one of these numbers before. So if I've ever computed the power of 5, and then I try to compute the power of 5 again, I don't need to go through the process of computing all the steps. I can just look up what is the power of 5. So when I'm computing the power of n, if I had already previously computed the power of 5, rather than go through all of these steps, I would just check, am I at 1? No, no, no. Oh, okay, I've solved the power of 5 already. So I can just return power of 5 plus whatever I have here in the count column. So that's why I'm keeping track of where I started, of what I started from with the key variable. And then I'm just going to have this loop while n is not equal to 1. I also thought maybe it's a concern that they would give me a negative number or 0, but their constraints say that n, or k as the case may be, or sorry, like their constraints say that low and high are going to be positive numbers. So I don't have to worry about having to compute the power of a negative number. And I think it's also guaranteed that there's always going to be some power. Like there is no number such that this just explodes away to infinity and never comes back to 1. While n is not equal to 1, what I'm going to do is first check to see if it's in my memoization dictionary. If it is, I'm going to do that step I talked about where I just return the count so far plus the count that I've already computed. And it occurs to me that in this case I can also just add self.memo of key. I should be doing this. Otherwise I'm not getting as much benefit out of the memoization. I can go ahead and store this value as well. Count plus self memo in. And actually, like, I guess this is the, let me just do this so I don't recompute the same value twice. Oops. Result is equal to that, and memo key is the result, and then I'll return result. So if I have the value that I'm currently at in my memoization dictionary, then I know what the answer is going to be. It's the count that I'm at so far plus whatever answer I have stored, and then I'm going to add that as the answer for my original key so that I don't have to go through however many steps I did to get this before. return that result. Otherwise, this line here, line 13, is where I implement these two rules, the even or odd thing. So this is saying in becomes in divided by 2 if in mod 2 is equal to 0. So of course in mod 2 means is it evenly divided by 2. So if in is even, it's going to become in divided by 2, and otherwise it's going to become 3 times n plus 1. So this line here is just implementing the two rules that were given. And then we're going to increment count, and count is just keeping track of how many steps I've had to take, how many times I had to implement this rule, and count is eventually going to be what they call the power. And so then line 15, if I've reached line 15, that means I've ran this loop over and over again until n became 1. I never found an answer in my memoization dictionary, so that means 1, I will store the count in my memoization dictionary in case I encounter this again in the future. And then second, I'll just return the count. So that's the power function, and it's basically most of the logic for this problem. The other thing I'm going to do here is just kind of implement the 4 steps I showed you on the whiteboard. So we're going to find the power of all the elements, we're going to sort it, and then we're going to return the case. So here my power list is a list of tuples or pairs, and the first element in the pair is the power of n, and the second element of the pair is in, and I'm creating a list for each n in the range of low to high plus 1. And you may wonder, high plus 1, that's weird. I thought so too. I think this problem is a little ugly in that they want you to be inclusive in the low to high range. So usually I guess I've seen ranges written where the high is the exclusive. So go between low inclusive to high exclusive. That, for example, that's how Python's range works. But they're giving it to you as a high is inclusive. So in order to just make that fit, I have to add 1 to high. So that, if we're given 12 and 15 as an example 1, we can get all the numbers between 12 and 15 and not just go 12 through 14. And in fact, they do the same thing with k, or a similar kind of thing. They're not 0 indexed. They want you to be 1 indexed, meaning if they want to, like if 5 was the first element in your list, and they wanted to get the 5, they would say get element 1 or get element 2. And of course, in pretty much every programming language, lists tend to be 0 indexed. So that's another just kind of like clumsy, inelegant, awkward thing. You can see in line 21, when I'm accessing k less 1. But whatever, that's just a kind of clumsy, random thing you have to do to solve this problem. So yeah, my power list is a list of pairs. As I said, first element is the power, second element is the, or I should say 0th element, having just said what I said. 0th element is the power. Then the next element is the in, or the integer value. And then I'm just going to sort my power list by the first element. I'm going to sort the power list by the power, but what I'm actually going to return is the k less 1, the integer value that corresponds to the power. That's in the kth position, or the k less 1 position. So again, here power list should be something like this. It's going to be a list of pairs. And what I do is I pick the kth, and then I pick the k sub 1, and I return that. Whoops. Of course, I wrote it backwards, or my illustration is backwards. But so when I implemented it when I drew it, I wrote the power in the 1 position. When I implemented it in code, I wrote the power in the 0th position. But it's the same thing. I hope that wasn't confusing. It sounded confusing to say. But so for test cases, they have a few examples, 5 examples. I thought their examples were pretty good. So they say, what if it's 12, 15, and you want the 2? When testing it, k seems kind of irrelevant to me on my approach because I have to compute all the values anyway, and I have to sort the list. So it doesn't really matter to me if you're finding the first one or the last one. If my algorithm has worked, k is arbitrary. But we can try different values of k. So their examples also have you try with k being 1. So 1 is the minimum value that k can be given their constraints. It's also good to test the maximum value that k can be. I don't think they have an example of that, but I added a test case for, what if we have a range of 10 to 20 and k is 11? So k being the maximum value and the minimum value, and then just some typical value. Then it's also good to test this case, example 5, what if you just have the maximum range, low to high? Just to make sure that okay, you can compute powers fast enough and you're not going to time out. So we're passing all of our test cases. When I submitted it previously, pretty similar runtime, I guess. Well, it halved the runtime, I suppose, to fix my memoization error. It's a pretty similar percentile score, I think. My previous one was something like 45, 48%. I'm not sure how people are going much faster than this, because I don't see what I could be doing that's too slow. I think you have to compute the power for each number. And I think I'm computing the power relatively quickly. There may be some kind of analytic insight you can get to solve this directly or by a formula. And if you could do that, then I could see being a lot faster, because then you wouldn't need to do any of the memoization. But I guess it doesn't immediately occur to me what that would be. Anyway, that's going to do it for me. I'm not going to try to figure out how to make it faster. Although as soon as I stop recording, I'm going to read the discussion section, which I think is always an excellent thing to do. To see how other people do it. Pre-compute and well, I'm not going to read this while I tape. So I'm solving LeetCode problems. If you enjoyed this, let me know by clicking the like button. If you want to see more LeetCode problems, go ahead and subscribe. Thanks for your time. Bye-bye.